So I thought I would give a really brief update to you guys on recent developments in Spack. It's a little weird not being able to hear everyone, but hopefully that works. I guess I can see everyone up in the corner. For those of you who aren't familiar with Spack, it's another package manager for HPC. It's used worldwide. I think Kenneth has a plot like this because I basically did the same Google Analytics plot as he did. These are all the places that Spack is used. You can kind of see more of a bias towards the US, at least at the moment, but a lot of the other places still appear there. I'm not sure I did the stats quite the same way as Kenneth, but I mean, at least you can see that it's widely used. We get lots of web visits, and the stats keep going up. So, I mean, it seems like the community is growing. We're pretty happy with how fast Spack has caught up. I guess I'll just kind of cover how it differs from EasyBuild, since I don't have a whole lot of time for just an overview. We want it to be easy to install. You basically just clone Spack. You source a setup in script. You don't actually even have to do that. You can just run the executable. And then you can install things with Spack install HDF5. One of the main differences between Spack and EasyBuild is that whereas with EasyBuild you have fixed configs with names that are sort of predefined, with Spack the packages are templates, and so you can say Spack install package name at version, and these can be flexible both for this and the dependency versions. You can say Spack install this thing with this particular compiler and with options. So that's what the plus threads is. The packages themselves they're templates, so they can have build options. You can say Spack install and inject flags into the build because we use compiler wrappers throughout. So that's another difference. The builds in Spack are basically you force the build to use our compiler wrappers, which allows us to inject our paths into the build, which means that the executables that we build will just work out of the box once built. And then on platforms like Cray, we currently support custom targets, so you can do optimized targets for things like Haswell. We're working on better target detection for things like Intel, so that we could potentially do, we could have the packages know whether they're being run optimized or generic, and that'll be relevant for binary installations. And then finally, you can do customizations on any part of the DAG. The syntax is recursive. You can say Spack install MPI links at version with a dependency, so that's mpitch, at particular version. And the packages are simple. They're based on homebrew packages. They're basically just classes that have an install method. Some of them, we have special subclasses for things like AutoTools builds and CMake builds. But basically, we define a DSL in pure Python that you can use to define your package build. I can get a little more into that later. I already kind of covered this, but here's some more examples of the kinds of things you can do with Spack. You can say with the dependency constraints. Unlike EasyBuild, Spack actually installs things into a database. So once you install something, you can do Spack list to see what's available. This is showing a really old Spack list output with 303 packages. These are just names. And for any of those, you can customize the install with Spack install and special syntax that we have. You can say Spack find to see what's installed after you actually install it. And so what you'll notice here is that with Spack find, it's showing you the packages that are installed, so the actual physical installations, grouped by the platform they were built with and the compiler they were built with. And so you'll also notice that these have particular versions that they're associated with. And that's because these are actual installations. They're not just the templates. These are instances of the templates. So you say Spack install ImageMagick. It goes and fills in all the details for the build according to what's in the repository. And you get a build of ImageMagick, say 6.89-10. Same for all the other ones of these. And this is only showing part of the information. So you notice that these two Dynance installations both have the same version. They're different in some other way, but we're just not showing you in the top level view. The find command supports queries, so you can query over these things to narrow down the versions. And you can also do things like, you can find specific package names and only list those parts. We go and search our database for things called call path. And you can do things like this and show the full dependency information. So you can say Spack find -dl call path. This is saying show me the dependencies and also the short hashes for the install. So that's cool because you can actually see what something was installed with, what it depended on. We track all the dependencies. If you try to uninstall something, will tell you that other things depend on it still. And you can see how these two installations actually differ. You can note that these were built with different versions of Boost. And so we make sure that the hashes are, these are computed from the entire subdag, and that allows us to basically build lots of ABI incompatible things with separate instances. Like I said, you can constrain versions of dependencies. I don't want to spend a whole lot of time on this, but if you suppose that the DAG looks like this for your build, and you want to install MPI leaks, you don't actually have to know anything about the structure of the DAG, just that it depends on libelf. So if you're trying to build something, you know that libelf version is what's causing you problems, and you want to change it, you know that 0813 is broken and you really need 0812, you can just say Spack install that thing with whatever compiler you want, and this version of that dependency, and it'll go and build that. The other kind of cool thing about Spack is, whereas EasyBuild has a tool chain, we have a notion of a virtual dependency. So different packages can provide an interface, and other packages depend directly on the interface. So things don't depend on mpitch or OpenMPI in Spack. They depend on MPI. And MPI is versioned. You can depend on MPI at 2 or higher, and different packages can provide MPI at that version. This slide didn't come out so good. Hold on, let me reduce that. Here. All right. And so what this is showing is, if you have this DAG, MPI leaks depends on MPI. When we actually go and concretize that, we basically resolve all the dependencies. We substitute this node with the natural implementation of MPI. And you can control that on the command line, and if you don't put anything, we'll just pick one. But here's how you install MPI leaks within Bappitch, and here's how you install MPI leaks with OpenMPI at something greater than 1.4. So this is like Python array slicing. And then finally, you can be non-specific. You can just say install it with some MPI2 implementation at the bottom there. And that's all encoded in the package file. So we know which MPI implementations provide which version of the interface. So if you want to think about what's happening in Spack, when we do this, we take this syntax on the command line, and essentially this is the root of the DAG. Each of the carets says it depends on this thing. These are just constraints on different nodes in the DAG. We take that and we normalize it, which means that we build out the DAG for that spec. It has partial constraints on it. We concretize that, and basically what this means is that we go and evaluate which things it could depend on according to how the packages are defined. Remember, they're templates, so that can vary. There's conditions and things. You can have different versions of the packages, and it's very easy to build something with, say, a different version of a dependency. We go and evaluate all those constraints, check them for conflicts, and we end up with a spec that looks like this, with all the information specified on it. And we can store that along with the build in a spec.yaml, and you can actually go and reinstall this thing again. If you send someone the spec.yaml, they can say spack install -f, that YAML file, to reproduce the build. So that's basically how Spack works. All the information in this YAML file is also stored in the database that you can query, and that's what Spack find is doing. It has all this metadata in it. And I'm not getting into things like build options here, but we have a pretty robust parameter system, so you can have things like what network interface does my MPI installation support. That can be a multi-valued variant, which is something new in the latest version, and so on. So we recently released Spack version 0.11. I'm not going to get into all the features of this, because there's a whole bunch of them. But basically, a year ago, we had 1,000 packages. Now we have over, actually, 2,300 at this point in the main develop branch. In the release, we have 2,178. The big things that we added for users this time are relocatable binary packages. So we actually support a build cache in sort of the way that Nix does, in the way that Geeks does. So we can make a binary package out of a particular Spack hash after it's installed. And on installation on another machine, we'll go and rewrite the RR paths so that it knows where to find its dependencies there. We're working on getting the relocation for compilers right. So currently this works for the system compilers, but not necessarily things like Intel. But we're working on auto-discovering things like the compiler runtime paths so that we can take a binary from one machine built with an Intel compiler or some non-standard, non-system compiler, like a newer version of GCC for C++ 17 or something, and relocate it properly on another machine. We've got full support for Python 3, so Spack will run just fine in Python 2 or 3. And then there's improved module support, and so you can basically make module files using templates. And we have a pretty robust YAML syntax for making LMOD hierarchical, LMOD module hierarchies. You can actually, in Spack, make a module hierarchy out of any virtual dependency. So if you don't just want core and compiler in MPI. You can also do core compiler MPI LAPACK or core compiler MPI BLOS or something like that, and put the actual other virtual dependencies in your module hierarchy. And if you go to the spack.readthedocs.io, if you look at our tutorial, in the module tutorial, there's some examples of how to do that. And it's pretty simple to define a module scheme. And it doesn't require writing any code. There's lots of improvements for packagers that we added. We added test dependencies. So we have lots of different dependency types like build, run, link. Test ones are basically build dependencies that only get loaded at test time if the package is going to run tests. And we added multi-value variants, which I talked a little bit about, but basically that allows you to, instead of having just plus or minus threads, which is a Boolean variant, you can have, my threading options are, say, OpenMP and P threads or something like that. It's up to the packager to decide what that means, but we support that, and we actually support depending on those. So you can depend on a package with one of those options enabled, and if it has, say, 2 of them, then that package will satisfy the constraint. And then finally, we added something that maybe people will have mixed emotions about. We have a package in Spack, QMC pack, that feels compelled to maintain a 40,000 line patch on one of its dependencies for some reason. And they really wanted to be in, yeah, I know, Kenneth is wincing. And so we don't condone that necessarily, but it's a pattern that we've seen before and that other packages wanted to do. So we actually add the ability to, for a package, so for the QMC pack guys to maintain the patches for their dependencies in their package file without interfering with other things that depend on the dependency package. So essentially what that means is you can say depends on some other package with a list of patches. Spack will go and fetch the patches. It'll take a content hash of the packages, or of the patches themselves, and it'll put it on the hash of the dependency package. And so that means that basically when you depend on something with a patch, Spack will make a special version of it just for you, just for your package that gets built alongside the others, and it won't interfere because these things can coexist because we RPath everything. So I think that's pretty cool. It enables us to at least package the ecosystem and then advise people not to do this stuff and that they're causing themselves more pain than maybe is merited. And so I think that's useful. It also enabled us to do things like HPC Toolkit maintains a bunch of packages on the various binary analysis tools that they have. So they're working on porting their little custom system to Spack because of this. And lots of speed improvements. And then there's a whole lot more in 0.11. So if you want to see the whole list, go to github/spack/back/releases and check out the full list. This is our first release in a year, but we're going to try to be releasing every month now, just on a clock instead of releasing infrequently like we did before. Okay, so all right. So I wanted to talk a little bit. I guess you guys have 4 minutes. So I'll see how long I can go. Spack is very closely tied, but not dependent upon the U.S. exascale computing project. And so for this project, basically, this is a collaboration of all 6 of the national laboratories, the big ones. So this is Livermore, Los Alamos, Sandia, Oak Ridge, Argonne, and Lawrence Berkeley, or NERSC is the supercomputing center there. And essentially, the exascale computing project, it's about 18 or 20 applications, big HPC applications that have lots of dependencies that they want to build on these, I guess they call them chip class machines. And so that includes like our Sequoia machine, our upcoming Sierra machine that they're citing right now, things like Titan at Oak Ridge and Corey at NERSC. And so they don't currently have a way to automatically test all that software on those machines. And so we're hoping to make that the way to distribute exascale computing program software. And so that includes actually a lot of stuff. The big items on our list for this year are, we'd like to be sort of a, DevRamp is the project that Spack is part of in ECP, so we can kind of ignore it. But we'd like to have a dependency model that can handle all the software that we see. I don't think we're quite there yet in terms of modeling all the different compiler intricacies, but we do have a pretty good dependency model in terms of things like MPI, like you saw. we'd like to have a hub for coordinated software releases so that the teams on ECP, so the different application teams and the different software teams will be coordinating their own releases. And we've had some groups like the math libraries use Spack to coordinate those releases so far. And I'll talk a little bit more about that. We want to do build and test automation for packages across facilities. So basically, we would like people to just get their package into Spack and they would get testing at the different HPC facilities for free. So they would get testing on a Boolean system, on a Cray system, on these GPU machines running on Power, maybe some ARM machines as well. And then finally, we're working on hosted binary and source distributions for all the ECP platforms. So what that entails right now is setting up some infrastructure in Amazon to actually host binaries so that, right now we have the binary packaging support, but we don't actually build the binaries or make them available anywhere. But we're hoping to have infrastructure so that we can put optimized binaries out there and have you just install them so that a Spack install takes seconds. If you're on at least a machine that we recognize. And then you would still be able to build the things that aren't included there. We've had a number of successes with different ECP applications. I don't want to get too far into this, but basically, we work with a lot of different people, including the XSDK team, which includes some of the big solver libraries. So the actual solver developers of Petsy, Sundials, Magma, Plasma, Charlinos, SuitValue, they work with us and they coordinate a release of this whole stack in Spack every so many months. And so we're working on getting this whole stack tested across these machines. The green libraries are the math libraries. And some of these are higher level, so like Fortran is actually I think low code, and Alchemia is some kind of library. But it's higher level, it's more of a physics library than a math library. MFEM's a little more developed finite element library. If you haven't seen mfem.org, check it out. It's pretty cool. Lots of interesting graphics. All right. And yeah, like I said, we developed that horrendous patch or that feature for the CPAC guys. We work with these guys and develop features for them when they need them. And so the collaboration is good with the ECP. Like I said earlier, the community is growing. We have contributors from lots of different places. These are lines of code in packages by organization over time. And so I think this is going from 2013 when Spack first started up to 2018. You can kind of see that the green up here is Livermore and the blue down here is Livermore. Spack was mostly a Livermore project up until about 2015, 2016. And then we really started getting community contributions and they've been growing steadily since then. Let's see. And sometimes they build things for us. So we had one of the ECP teams was trying to put all the ECP proxy applications into Spack, and these are like little benchmark codes that represent some kind of physics that people want to experiment with on machines for performance or for different application design decisions. We talked about tagging them to differentiate them from the rest of the packages, and so one of our EPFL contributors, EPFL actually uses Spack to manage registers, added tagging capabilities to Spack that day with a pull request. So we were like, okay, I guess we can do that. So the community has been really beneficial for us too, which is it's something that we share with EasyBuild, not the actual community, but the fact that we have communities. And yeah, next things that we're going to be working on. Two big things right now are the binary packaging that I talked about. We're working on hashing out the details of that, and better models for dependency management for developers. So if you've used some of these language level package managers, like say Bundler or NPM or things like that, where you can have basically a requirement file at the root of the repository, or some people call it a manifest, where you say, I depend on this thing at this version, this thing at this other version. We'd like someone to be able to clone a repository that has a Spack file at the root and just say Spack install and have their dependencies built for them in a little environment right there. So that essentially it would be very easy to clone someone else's HPC application and start working. So we're adding something kind of like virtual environment support to Spack, as well as better dependency resolution to support this. So expect to see something like a YAML format that would go at the top of a repository, maybe with some compiler hints for where to find compilers on different systems and things like that, since Spack can actually fetch system compiler.
Cutting us off?
Yeah.
Spack. we're putting something based in, and am I still good, or do you guys have to leave? Okay. Yeah, so we're adding stat-based dependency resolution. It's a little more complicated for Spack just because of the complexity of the dependency model. It's not just packages and versions. Like this is typically formulated for other package managers. It's package, version, variants, which are basically other arbitrary parameters, compilers, rules about the compilers, and things like that. I'm going to talk a little bit more about this at FOSDEM on, I guess, Sunday at the Package Management Dev Room, but one of the things that's complicated about developing a concretizer for Spack is that we have to support cross-compiled machines. And so there are things that you have to do there that you wouldn't otherwise have to do in your dependency resolver. So if you can imagine, like, if you're in Ruby, your package, it's just a package in a, because there's no compilation, there's no anything that depends on the architecture. If you're in Spack, and you build on a machine like Cori, where the back end is a Xeon Phi, and the front end is maybe a Haswell, or something like that, you can't just build the whole thing for the back end, because the back end binaries won't run on the front end. And so we have to actually treat the build dependencies and the link dependencies separately in the concretization DAG and build two versions of each thing, one for the front end and one for the back end. So if something is both build and a link dependency, then for a non-cross-compiled build, we would basically just build that once, the architecture we're running on. And for a cross-compiled build, we have to build it twice. So we're working on splitting that in DAG. I can talk for a lot longer about this, but it looks like I have to go. So thanks.
Yeah, thank you very much. Hope to see you next time.